Hi, in this video I will introduce some of the core tools of our framework. If this work interests you, you will be able to join one of our workshops either in person near Paris or online. The core tool of our framework is finite automata, a fundamental object in theoretical computer science. Here is an example of a finite automaton. You can see states represented as circles and transitions between states represented as arrows. Each transition has a label which we call a letter. For example, if I take the red transition from state Q to state P, I read the letter A. You may also notice that state Q has a single incoming arrow with no origin. This indicates that Q is an initial state, the stage where the automaton can start its run. A run of an automaton is simply a sequence of transitions starting from an initial state. For instance, I start in Q, I read A and move to P, I read B and come back to Q, and then I stop. This sequence is one possible run of the automaton, shown below. In our framework, we adopt a common idea in psychology which was introduced by Jerry Fodor, which is that the mind can be understood as a set of interacting modules. We model each module as a finite automaton. A module can evolve on its own or interact with other modules through communication. Let's see how this works. On this slide, you see two automata. Together, they form what we call a system. A state of the system is not a single state from one automaton. Instead, it is a pair of states, one from each automaton. From such a pair of states, two kinds of transitions are possible. First, synchronized transitions. If both automata share a common letter, they can take that transition simultaneously. For example, from the state QP, both automata can read the letter A at the same time. This brings the system from QP to RS. Second, unsynchronized transitions. If a letter exists in one automaton but not in the other, only the relevant automaton moves. For instance, from QP, the first automaton can read the letter B because the second one has no transition labeled by B. The system then moves from QP to RP. What is the psychological interpretation of a system? In this framework, a system of communicating automata is a psychological theory. Each automaton represents one module or a part of the environment. States and letters of each module represent psychological concepts. Here, for example, we model a simple stress mechanism. The system enters a state called stress when danger arises, and leaves it when danger is no longer present. Let us now talk about refinement. Refinement is the process of making a theory more precise and more accurate. We define 8 refinement operations, including, for example, adding a letter, adding or removing transitions, splitting a state into more detailed states, or even adding a new automaton to represent a module. For instance, if I use the previous automaton of this theory of stress, and I wish to have a more precise notion of stress, I can then refine the state called stress into 2 states, small stress, large stress. I do this by using the refinement operation called splitting a state. These operations allow us to move gradually from a vague theory to a precise one. We prove 2 key mathematical properties. First, when a system is refined, all its possible runs are included in the runs of the previous system, up to a relation. Intuitively, refinement restricts behavior. It does not invent new unexplained behavior. The second mathematical property is that starting from a trivial system With one automaton composed of one state and one single tool loop, we can construct any system using refinement operations alone. We call this property completeness. This leads to a concrete methodology for theory building or theory translation, which is to translate a verbal theory into a formal model. First, I begin with a trivial system. Then I pick one concept of the theory which I wish to model. I use the refinement operations to model this concept, and step by step we either make a previously modeled concept more precise, or we add a new concept to model. The resulting system is the theory. There is one final step which I will not detail here, which is called verification. Using logical formulas, I can verify whether a system satisfies specific theoretical requirements. This provides us with a second way to ensure that our system corresponds to what we are intending to model. Why does this matter? Throughout the construction process, the formalism forces two things. The first one is that concepts must be completely unambiguous. The second one is that every theoretical step must be completely specified. Very often, this reveals conceptual ambiguities or parts of the theory that were not completely specified. This allows, in turn, to formulate new research questions. Sometimes, new properties of the theory are found that are logical implication of expressed properties. Now, if a theory requires it, it is possible to extend this framework in the following way: by adding continuous time, continuous variables, differential equations, or even probabilities. We will host an in-person workshop and an online workshop where participants will learn how to build formal theories using this framework. If you are interested, I recommend choosing a theory that has more or less explicit notions of states, transitions, steps, or actions. Thank you for watching, and I hope to see you soon.